Hello friends, welcome back. My name is Mohsin Mullah, and in this particular video lecture we are going to see about solution methods for unit commitment problems. Okay, so like in the previous video lecture we have understood what is unit commitment and how to select number of units to commit for a particular load demand depending upon the variation in the different load demands depending upon the various activities conducted during all the time of the say day, week, month or year. Okay, so now we have to select a set of you can say units as a combination to commit to that particular load. So we have to decide how to do that selection. So therefore here we are going to see some of the methods used for the solution of this unit commitment problem, because which particular combination of unit is going to be you can say most economic. So we have to determine based on, we can say, their economic operation conditions, or the you say the overall cost of operation, so that needs to be considered. And then the final commitment, you can say, we have to assign to that particular set of units. So here basically there are you can say three methods that we are going to see. So the first method is the simplest one, which is priority list method. Then there is a dynamic programming method for more complex, you can say, combinations. Then there is a Lagrangian multiplier method also that we are going to consider. Okay, so now let us first consider the priority list method. Okay, so previously we had taken one example, say while discussing about the unit commitment, I think in the lecture number 14. So here what we had done, so here we had seen the concept of unit commitment, and also based on say the fuel consumption equation of the three units, we had determined that whichever units are most economical, those units will be kept on for all the time, and those who are least economical will be turned off first. So based on their calculations here, so we had determined that for highest load all the three units will be turned on, and then when the load is decreased considerably, say up to when it is below 800, then only unit number 1 and 2 are operated, unit 3 will be shut off. And then uh, here below 1000, okay, sorry, below 1000, so this unit 3 will be shut off. Then up to 700, so unit 1 and 2 are operated. Then after you can say below 700 megawatt of the load, only unit 1 is used to supply the power. Okay, so that is what we had seen. So this was just based on the basic equations given, and from that we had tried to obtain the fixed component, and depending upon the components of p1 and p2, sorry, p1 and p and p square, we can say in general. So we had tried to determine that you can say combination. Now when we want to you can say do it more efficiently, then we need to know the production cost of the units as well. So here we are going to consider here to understand the concept, we are going to take the same example of the one plant operating with the three units, and again the equations of that particular plant are same equations here. So first unit is having minimum of 160 megawatt, maximum of 600 megawatt. Then its a fuel consumption equation is 600 plus 7.1 p1 plus 0.00141 p1 square. Then unit 2 is having minimum generation is 100 megawatt, and maximum generation of 450 megawatt. And then its fuel consumption equation is given by F2 equal to 350 plus 7.8 P2 plus 0.00195 P2 square. Okay, then unit 3 has got minimum of 50 megawatt, then maximum value of 250 megawatt. Then its fuel consumption equation is F3 equal to 80 plus 8.0 P3 plus 0.0049 P3 square. Okay, so these are the basic, you can say, equations known for those three units. And along with that, now here to understand the overall operation, or you can say overall selection of the most economic units, so here we need to consider the fuel cost also. So let us take the fuel cost here for each of the unit. So for the first unit, so I'll write this as fuel cost of first unit equal to rupees 1.1 1 per mega BTU. Okay, so million, you can say million British thermal unit. BTU is British thermal unit. This is used for basically to obtain the heat out of that particular fuel used for burning the, or you can say for heating the water in the boiler. Okay, so whatever heat is produced, so that cost is 1.1 for every million British thermal unit. Okay, so now similarly for the second unit also the cost is given here. So that cost is given as rupees 1.0 per MBTU. Then similarly fuel cost of unit 3 is rupees 1.2 per MBTU. Okay, so if this is given, then we have to determine which of the units should be operated, okay, mostly kept on, and which of the units are to be turned off when the load is reduced. Okay, so now let us try to obtain that. Okay, so here let us find the average cost for 3 units. Okay, so here I will write the average cost for the 3 units is calculated as follows. Okay, so let us for consumption of certain 1 megawatt of power, so or you can say for production of 1 megawatt power, how much fuel it is going to consume, and what will be the overall cost, average cost for that 1 megawatt hour power. Okay, so now let us try to obtain that. So here what is known to us, F1 is given, which is having the 600 plus 7.1 P1 plus 0.00141 P1 square, it is given, and let us take that P max for this particular unit is given as 600 megawatt. Okay, so now substituting that P max value, 7.1 into 600 plus 0.0141 into 600 square. So simplifying this, we are going to get around about the 600 here plus 4260 plus 507.6 here, and totally we are gonna get 5367.6 MBTU. So here it is per hour. Okay, so this equation is for fuel consumption per hour. So here MBTU per hour we got. Okay, so now what will be the cost for this amount? So let us calculate that one. Hence full load average production cost is full load average production cost is equal to, so whatever here units per hour produced, okay, into the cost per MBTU. Here we have to take per MBTU, it is 1.1. okay, and overall 600 megawatt is produced. So here we are going to get the value as rupees 9.84 per megawatt hour. Okay, so this is what we got for unit 1. Similarly for unit 2 we can obtain F2 is given as 350 plus 7.8 into P2 plus 0.00195 P2 square, and here P max is 450 megawatt. For the second unit, maximum power generation capacity is 450 megawatt. Okay, so now let us try to calculate again the average cost here. So let us first substitute this 450 megawatt, and let us see what is the total units produced. So 350 plus 7.8 into 450 plus 0.00195 into 450 square. So finding out this value, it will come around 4254.87. okay, and now considering the average cost here, hence full load average cost is equal to 4254 into here the cost divided by, here it is cost is rupees 1. okay, it is rupees 1 for the second unit, and maximum megawatts generated are 450. so therefore what we're gonna get from here is 9.455 rupees per megawatt hour. so here average production cost is 9.455 per megawatt hour. Next is for unit 3, F3 equal to 80 plus 8 P3 plus 0.0049 P3 square. okay, then Pmax for this particular unit is 250 megawatt. so substituting that maximum value to 250 plus 0.0049 into 250 square. so solving this, we're gonna get 2386.25. okay, so now average hence full load average production cost is equal to, so this units into number of these are nothing but the million BTUs. okay, so this value is nothing but per hour. okay, so here also I think I have not written the unit, you can write here BTU per hour. so this into the cost here is for third unit 1.2 per MBTU. so let us multiply that value, then divided by the overall generated megawatts, 250 megawatts. so therefore here what we gonna get value as for this production cost is 11.45 rupees per megawatt hour. okay, so here we got the average production cost for the 3 units. so for the unit number 1 it is 9.84, then for unit number 2 it is 9.455, and for the unit number 3 it is 11.45. so basically here the lowest unit is the second unit 9.455, and second most economic unit is the unit number 1 9.8584, then the least economic is the unit number 3 11.45. okay, so first turn off should be for unit number 3. okay, so now let us try to give the priority list here. okay, so therefore the priority list for the 3 units based on the average production cost is as follows. let us put here in the form of a table. okay, so let us first take the units. then their production cost, then minimum megawatt, max megawatt. okay, so first we have to take the most economic unit number 2 with the lowest production cost. and its minimum is 100 and maximum is 450. Then next most economic is unit number 1 with 9.8455. Then minimum is 160 megawatt, maximum is 600 megawatt. Then least economic 11.4550 minimum and 250 maximum. Okay, so this is what the priority list we get from the analysis by considering the average production cost. So in the first case where we had discussed about the unit commitment, so we had just used the available information, that was the fuel cost equation. So depending upon the three components of the fuel cost equation, we had determined a particular list. So here, since the production cost is known, so based on that production cost we can determine the number of units, or you can say order of the units to be kept on. Okay, so here basically we are going to consider this you can say methodology, so depending upon the load value. So also here we need to assume something, so assuming the startup cost minimum up or down cost to be negligible. Okay, so that we need to consider here, negligible. Okay, so the unit commitment scheme is as follows. Okay, so now let us consider the combination. So here the combination, so minimum megawatt from combination and here maximum. So here we'll consider the load is highest, then we'll decrease the load to the lowest. Okay, so that way we will be able to get the you can say right kind of committed combination for supplying maximum to minimum load demand. Okay, so now maximum will be when all the three are operated. So first unit 2 is operated, then unit 1, then unit 3. So these three are turned on, so their minimum needs to be added together. So minimum values are 100 plus 160 plus, so 100 plus 160 is going to be 260 plus 50, so it is going to be 310 megawatt. Okay, then maximum is going to be 1300 megawatt. Okay, then next economic are 2 plus 1, so first unit number 2 and unit number 1. So that time if you add the two units total value, so unit 1 and unit 2 together, it will make 260 minimum, 260 megawatt they are going to supply, and maximum, adding their maximum values 450 and 600, so it is going to be 1050 megawatt. And finally unit number 2 only has to be kept operated because it is most economic, so in that case its minimum demand will be 100 and maximum will be its maximum capacity of 400 megawatt, 450 megawatt. Okay, so this is what we get as the final unit commitment, you can say scheme or schedule. So first combination is 2 plus 1 plus 3, second combination is 2 plus 1, and third combination is only 2. So these three combinations are available here. So for supplying the load between 310 to 1300 megawatt, so first commitment is, first combination is, so here combination first combination is selected to supply the load between 310 megawatt to 1300 megawatt. Then when the load is between 260 megawatt to 1050 megawatt, only 2 and 1 unit are sufficient to supply that amount of load. And when the load is very low, like 100 megawatt to 450 megawatt, so in that case only unit number 2 is to be committed. Okay, so that is how we have to determine the different unit commitment problem here. Okay, so this is it in this particular video lecture. So I hope you understood the concept of unit commitment when we are considering the average production cost. So I'll see you in the next video lecture. So till then, happy learning and thank you.